There are two core practicals we need to do for rate of reaction. The first one is involving a reaction that gives off a gas as a product, and we collect that gas and monitor and see how quickly we're collecting it, and by doing that we can make a judgment on how quickly or slowly the rate of that reaction is going. Now, there's a couple of reactions you could do. The one in the book is with magnesium and hydrochloric acid. There's another one which is equally common to do at GCSE, which is calcium carbonate and hydrochloric acid. So I'm going to do the calcium carbonate and hydrochloric acid one in the video here. We'll do hydrochloric acid and magnesium in a lesson. It's the same thing, just to get, so you can see a couple of different examples. So I'm going to react 50 centimetre cubed of hydrochloric acid. I'm going to use 10 grams. I'm going to use 10 grams of calcium carbonate. Okay, so I'm just going to do that different. So same reaction, different reactants. In the experiments, the calcium carbonate is present in excess, so it's going to be the CaCO3 is present in excess. Excess means too much, and basically we're going to have too much of the solid to make sure all the acid reacts. Okay, so I'm going to put, instead of putting magnesium in the conical flask here, I'm going to put the calcium carbonate in the conical flask. I'm always going to measure out 10 grams. And we're going to react it, and we're going to collect the gas over water. This technique is where we put the measuring cylinder or indeed any container, fill it with water and put the delivery tube underneath it, and the bubbles obviously rise up through the water, pushing the water down. This is called collecting a gas over water, and we can measure off on the measuring cylinder how quickly the gas is being produced, maybe every 30 seconds or so. Now we're going to do this experiment, when you do it in class, we'll probably do it 5 times. I'm going to do it twice. I'm going to do experiment 1, okay, is going to be with 50 centimetre cubed of 0.5 mole per decimetre cubed acid and 10 grams of calcium carbonate. And experiment number 2, I'm going to do it twice, as I say, is going to be exactly the same volume, 50 centimetre cubed, this time of 0.1 mole per decimetre cubed of acid. So in other words, I'm changing the concentration of acid. I'm going to keep the calcium carbonate the same, so we only change one thing. We're going to use exactly the same volume of acid, different concentration. We're going to see how that affects rates. Now I would imagine, you would imagine, I'm sure, the higher the concentration of acid, the faster the reaction goes. So before we start the experiment, the first thing we need to do is construct a results table. So we need to decide what readings we're going to collect, and we also need to have somewhere ready to store that data so we can collect it and not get confused. Now, rate of reaction is best to measure it at the very start of the reaction. Reactions are fastest at the beginning because the most particles are present at the beginning. As the reaction wears on, the particles react and get used up, if you like. So we could say just take reading after 30 seconds in both experiments, and that would give us an idea of how quick things went. I guess the problem with that is, what if that reading after 30 seconds is anomalous? If we only take one reading, we won't know. So we're going to do this experiment for 4 minutes. Okay, so the first column we need down here is a time column. Okay, and we're going to do it for 4 minutes. So time. Okay, and we'll do that in seconds. We'll record it in seconds, but we'll do 4 minutes worth, as I said. Okay. Then after that, we're going to have concentration over here. So we're going to do this twice. We're going to do it, well, when you do it in the lesson, you can do it 5 times, but we're going to do it twice here to keep the video a little bit short. We're going to do 0.1 mole per decimetre cubed acid. And we're going to do 0.5 mole per decimetre cubed acid. Okay, and what we're going to do is we're going to look at the volume of gas they're given off. So overall here, we want to measure the volume of gas, because that's how we are going to measure the rate of reactions, by seeing how quickly the gas is coming off. And that volume of gas is coming off in centimetre cubed, so we'll put that down there as well. Okay, so let's just quickly do 2 columns here, and then we're ready to go. So yeah, we're going to do it for 4 minutes. So we need to have several rows ready to go here. Now we've ruled off the all the results table there. Let's put the time in. So 0 seconds. We need to take a 0 reading, and we go 30 seconds, 60 seconds, 210, and 240 is our 4 minutes. Now they may not last 4 minutes, but we've got 4 minutes worth of readings we can take there. So we've got the experiment set up and ready to go here. We've got the calcium carbonates, the marble chips in our conical flask. I've got a results table and a stopwatch. I've filled our measuring cylinder here brimful of water. So it's ready to go. Now there are a number of errors and sources of problems with this experiment. The biggest problem is I've got my acid here, I'm about to tip it in. When I tip it in, if you remember, the reaction goes quickest at the start because this is absolutely rammed full of acid particles now. As the reaction goes on, those acid particles are used up. So as they're used up, there's less collisions as time goes by. So this is quickest at the start, and as we tip it in here, then the reaction goes quickest and the bung is not in there. So it takes me a moment to get the bung in, so there is a source of error there. Give it a stir at start the stopwatch. Okay, and we're now collecting our gas over here. So we're going to collect our gas every 30 seconds as time goes by. You'll see that bubbling away. Okay. Now, ideally we'll stir every experiment the same, because the more we stir it, the faster it goes. So, coming up to my 30 seconds, 27, 8, 29. So now I'm 30, so I'm going to collect my reading. That's reading 22 centimetre cubed of gas. That's my 22 centimetre cubed gas. So I'll write that down there. And we're going to carry on doing this, taking readings, maybe swirl it once every 30 seconds for 4 minutes. We'll take a next reading on the 1 minute mark. So it's now coming in at 36. Just taking the last reading now, up at our 4 minutes, so we're coming in at about 140. So 140 is our final reading for that experiment. So now stop that and start the next one up. So now set up second experiment, this time with 0.1 mole per decimeter cubed hydrochloric acid. Same 10 grams of calcium carbonate. Now you'll notice this time I have a gas syringe here. So I'm not using an upturned measuring cylinder, I'm not collecting over water, I'm going to collect the gas using a gas syringe. Exactly the same idea as before, just a different, much more accurate piece of kit to collect the gas. So let's get started. Again, we'll tip in the hydrochloric acid, put the bung in, start the watch, and get started. Now, this should go noticeably slower, okay, because the acid is more dilute. Now, the other thing about using a more dilute acid, in more dilute acid there are less acid particles present, so we should get less collision, so the rate should be slower at the start. The other thing about using less acid particles, same volume, don't forget, it's just less dilute. Okay, more dilute I should say. The other thing about using a more dilute acid with less acid particles is we will get less gas produced at the end because there's less particles hanging around. And that's one of the reasons I can use the gas syringe. The gas syringe will measure up to 100 centimetre cubed of gas, and in the last experiment we produced far more than that. So first 30 seconds, it's about 3 centimetre cubed of gas. Okay, give it a stir again. And we'll collect next reading in just a moment. So the experiment's been running about almost 4 minutes now, about 10 seconds left. So see if we can just take one final reading on the 4 minutes on the gas syringe. Move that a bit closer, and that looks to me to be reading about 22 centimetre cubed. So that'll be where we finish that, 22. So we're ready to plot our graph now. I've already drawn up the axes. I've got time on the bottom. We decide to take time every 30 seconds. So we decide to take the volume of gas every 30 seconds. So the one that we decide time every 30 seconds. The one we decide to do in this fairly even increments, this always goes on the bottom. We didn't know what the volume of gas was going to be, so the one we don't know what it's going to be, that goes up the side. So let's start plotting our data. I'll do the 0.5 mole per decimetre cube one first. So at 30 seconds we had 22 centimetre cubed gas, so 0 was 0, put an X there. 30 seconds was 22, so that's each little square now, because there's 5 squares for 10 on the volume of gas. Each little square is 2, so let's bang on that 22 there. 1 minute was 46, so 60 seconds is 46, so 42, 44, 46. That's going to go there, and we keep on going like that. So just finished plotting that first 0.5 mole per decimeter cube graph, and it's a fairly classic rate of reaction curve. So it starts off quite steep, and then it starts to curve off and flatten off as the reaction finishes. So this is going to be a freehand curve, and line of best fit. It doesn't look like there's too many anomalies there, so we can probably mainly trace through those points like so. It flattens off at the end. Next curve is the 0.5 mole per decimeter cube, sorry, the 0.1 mole per decimeter cube. We're going to do that on the same axes, okay? So we want to compare both graphs. So first at 30 seconds we had 3 centimeter cubes, so a very different gradient on this one, much shallower. That's to be expected. The weaker the concentration, the shallower the gradient. 60 seconds was 5, so like so, and we'll carry that on. And the last X over here for 4 minutes was 20, so we'll put that there. Now again, we've got a much shallower graph here, and it would be a curve again if we could see that exactly, but it appears mainly as a straight line. So you could draw that, I suppose, with a ruler, but we'll do it as a curve freehand like so. Okay, so when was each reaction quickest? Answer, they're quick at the start. And when was each reaction slowest? At the end. And that's because the acid particles are being used up as the reaction goes on. Use the graph to work out when each reaction stops. Well, we can't really see with this one because it is still increasing. So that reaction was still going on. So that hasn't ended. Hasn't ended. We can tell when they stop because if you look here at this one, it goes flat at this point. It goes flat. The curve goes flat, and I probably could have improved that. I might even get a rubber and improve that end of that curve. So I'm just going to rub this last bit out. So if we look really close here, my line of best fit's gone above that point, that point, that point. So it's not ideal at the end. It's going all right until then. So I'm just going to rub the line of best fit out. And again, this is another reason we just do graphs in pencil always. So we can have a go at it. If we make a slight mistake, we can have a go at improving it. So we're going to, and the aim is to flatten that out there. So I'm happy with that. Now that experiment has, where the curve goes flat, where no more gas given, that tells us the reaction has finished. So I'm going to rule down from there at this point. The second that curve goes flat, I rule down, comes down at 210 seconds. So the 0.5 mole per decimeter cubed experiment ends at 210 seconds. How does the curve of the reaction appear when the reaction is going steep? Quickly, the answer is steeply. Okay, so with all rate of reaction graphs, when the curve is steep, it's fast. When it's shallow, it's slow. Right, so the next thing we need to do is use our graph to calculate the rate of each experiment. Okay, so to do this, we need to use the graph and we need to use a bit of maths. We need to calculate the gradient at the start of the reaction. Now, gradient is, in maths, the difference in the y-axis divided by the difference in the x-axis. Now, we calculate the gradient of a straight line. So this is really important now. I'm going to do this in pen. Now, I don't want you to do it in pen on your graphs, simply because it's just, it's impossible to rub it out, okay? But what we do is we take our ruler and we put it on these are curves. So we put it on the curve at the start. We put the ruler on at the start of the curve and imagine it's going in a dead straight line. So that's what I've kind of done there. Now this graph obviously curves off, doesn't it? It starts off steep and then curves. So I've drawn that as a dead straight line. Now anywhere where it's convenient now, we can take readings from that straight line. So I'm going to take it at 90, I think. I'm just going to draw it at 90. I could do it at 60. Because it's a straight line, it's all the same gradient. It really doesn't matter. I'm going to do it at 90. Okay, and I'm going to rule up to that straight line now. Again, pencil's better because it means we don't make mistakes. It's just I'm conscious the pencil won't show up very well on the video, so hence I'm doing it in pen. And where it gets that straight line, we rule it across here. Okay. Now that's coming in there at exactly 78. 78. That's coming in there at 78. And that was 90 down there. So my x-axis is 90, my y-axis is 78. Back over to this side. So it's 78, the difference in the y-axis. We started at 0, so 78 minus 0 is 0, so we take the difference. And the y-axis is 90 minus 0, so 90. So we need to do 78 divided by 90. So we've got my calculator, let's just put that down there. So we need to do 78 divided by 90 equals 0.86, 0.86. So the answer is, the rate of that 0.5 mole per decimetre cubed, the 5 molar reaction is 0.86. Now we need a unit. So the unit was, this is why we write them on the graph, centimetre cubed was the y-axis, seconds was the x-axis, seconds was the x-axis down there. So it is 78 centimetre cubed divided by seconds, so it's centimetre cubed divided by seconds, centimetre cubed per seconds. So you could write it centimetre cubed second minus 1. That is exactly the same as that. But either way, the rate is 0.86 centimetre cubed per second. Why does the rate of both reactions change as time increases? The answer is the acid particles are being used up. As the acid particles are used up, there's less collisions, so the rate gets slower. Let's just quickly write that in there. As time goes by, acid particles react, so there are less of them. Less particles equals less collisions equals slower. And that's why we get this curve on the graph, because the reaction slows down as time goes by.